Welcome to my channel. In this video, I'm going to solve all the daily LeetCode problems from February 2025. I'll walk you through my thought process for tackling different problems, and hopefully you'll pick up something useful along the way. Most importantly, I'd love to hear your thoughts. Share your ideas or alternative solutions in the comments below. Now, let's jump into it, shall we? February 1st kicks off with an easy one. Just check the parity of each pair and return the answer. Day 3 brings an interesting one. Each iteration is about testing the longest size we can get. On the next day, we got a classic greedy problem. Keep track of the maximum cumulative sum and update the answer along the way. Here's an easy but practical one. The key takeaway is the if-else-if trick, super useful when you only need to track two candidates in linear time. The next problem asks us to count tuples where two pairs of numbers share the same product. The idea is simple. There are 8 tuples for each case where a multiples b equals to c multiples d. With that being said, we can use a counter to track how often each product occurs, and then apply combinations to calculate how many pairings we can form. Multiply that by 8, and we get the final answer. On the next day, we got a medium problem. Since each ball has a distinct label, we can use it as a key and keep track of how many unique colors remain. That gives us the answer for each query. The next problem is to design a number container system. Whenever I'm asked to find the smallest or largest element, a heap or a sorted list usually comes to mind. Here, we use sorted list, which lets each update and query run in logarithmic time, making it easy to quickly find the smallest index for any number. The next problem highlights a neat idea. Sometimes it's easier to calculate the total and then subtract what you don't want. It's a simple but powerful trick worth remembering. Here, the idea is straightforward. First calculate the total number of pairs, then subtract the good ones. Good pairs share the same value of I, nums, I, so we can count them with a counter. The rest are bad pairs. The next day we got another problem that can be handled by stack gracefully. On the next day, we got a practical problem for heaps. Just keep in mind that different languages implement them differently. For example, Python's heap is a minute heap by default, while C++ uses a max heap. We've seen how prefix sums let us get range data in constant time. This problem takes it further with prefix products, where we can also compute the cumulative product of any range in constant time. This problem is a nice exercise for backtracking. Whenever a task involves splitting digits or generating all possible partitions, the input size is usually small, a strong hint that backtracking is the intended approach. On February 16th, we get a relatively complicated but interesting backtracking problem. Since we are asked to return the lexicographically largest sequence while making sure each number appears in the right distance apart, the trick is to place larger numbers first and use DFS with a mask to avoid reusing them. If a placement doesn't work, we backtrack and try the next option. On February 18th, we got a neat greedy problem. The trick is to use a stack, keep pushing numbers, and whenever we see an I or reach the end, pop everything into the result. The reason this works is that popping flips the most recent decreasing segment into an increasing one, which gives us the smallest possible arrangement in lexicographical order. On the next day, we got a fun problem, and I want to revisit this concept we mentioned earlier. The key idea is simple. Generate all possible binary strings of length n. Compare them with the original set of strings. The difference gives us the missing one. It's a neat reminder that sets are perfect for handling uniqueness and differences. On February 19th, we got another backtracking problem. What's nice here is that it follows the classic template. 1. Build the string step by step. 2. Prune whenever the current choice is invalid. And 3. Stop once we reach the target length. It's a clean example of how reusable the backtracking pattern is. It's highly recommended to practice this one. The next problem may look tough, but don't worry, we only need to clarify two key ideas. What does a pre-order traversal tell us about the tree? What do the dashes, the depth markers, tell us about the tree? Pre-order traversal always visits nodes in the order: parent, left subtree, right subtree. This ensures we know which node comes first, but not where exactly it should be placed in the tree. Without extra information, the same pre-order sequence could represent very different shapes of trees. That's where the depth comes in. The number of dashes tells us the level of each node, so we know whether it belongs as a child of the current parent, or if we should go back up and attach it higher in the tree. To reconstruct the tree, we pair each node with its depth, and use a stack to keep track of the current path. Each time we process a node, we pop from the stack until its depth matches, then connect it to the correct parent. This way, the stack naturally guides the reconstruction. The next problem is a great opportunity to understand how pre-order and post-order complement each other. In pre-order, the root node is always the first element. In post-order, the root node is always the last element. With this in mind, we can reconstruct the tree by following two principles. Pre-order tells us where to start building. Post-order tells us where a subtree ends. Since these two traversals compensate for each other, we can choose either approach. In my solution, I started from the post-order side. The next problem is a practical example of an advanced DFS technique. When solving it, the key question is, what should our recursive function return? In this case, our DFS needs to keep track of two values. 1. The maximum profit Alice can gain from the subtree, and 2. The timestamp of when Bob reaches the current node. By comparing Alice's step count d with Bob's distance dist, we can decide. If Alice arrives first, she takes the full profit. If they arrive at the same time, she only takes half. Otherwise, she gets nothing. The next problem is a good example to explain why we often take results modulo 10 to the power of 9 plus 7. It's because the count can be huge. This large prime is a standard contest modulus, and here it simply keeps the result bounded as the problem requires. Now the key idea, parity check. At each index, if the current prefix is even, it forms odd sums with all odd previous prefixes, so we add count odd to the answer and record one more even prefix. If the current prefix is odd, it forms odd sums with all even previous prefixes, so we add count even and record one more odd prefix. The next one is easy. We simply keep track of currently max and minute sum and compare their absolute values. Interestingly, LeetCode has given us some solid backtracking problems to practice this month. My approach is to recursively generate candidate sequences. The key trick is to keep two rolling values a and b and update them in place as b and a plus b, just like the constant space Fibonacci solution. Finally, we reach the last problem of this month, and it's a hard one. This problem is a follow-up to longest common subsequence. The DP table is helpful since it tells us how much the fronts of the two strings can share. Think of it as an overlap score. Then we walk the table from the bottom right to the top left. If the two letters are the same, we keep one copy and move diagonally. If they are different, we look at the bigger neighbor, up or left, move that way, and add the letter from the other side, because that one can't be shared. When one string runs out, we just add whatever is left from the other. By always following bigger numbers, we keep the most shared letters, so we add the fewest extras. That's why the result is the shortest common supersequence. That's it for today's video. If you enjoy this one, please like, share and hit the subscribe button. I will see you in next one.